So the next topic we're going to be looking at is exponential functions, and we're also going to be looking at logarithmic functions, which are inverses of exponential functions for the next topic, for topic 16. For topic 15, we're going to break into 3 videos, and the first video is going to focus on the graphs of exponential functions and how we transform those graphs. So as the basic introduction to exponential functions is going to look like a b to the x type of a guy. So this is the base b, and the hallmark of the exponential function is that the variable is in the exponent position. This is the hallmark of an exponential function. The variable is in the exponent position, and there's some restrictions that we have on b, and these restrictions are actually really important. So b has to be a non-negative real number, with the exception that it can't be 1, because if b were 1, you'd have 1 to the x, but 1 to the x is going to be 1 no matter what value you select for x, so you would wind up getting a graph that looked like y equal to 1, which is actually a linear function. So the base 1 is excluded. Negative bases are excluded. If you try to put a negative number in the base position, the graph of it is what I call a crap show. So exponential functions, base has to be a positive real number, except you can't use a 1, and the domain of the function is any real number you want to put into the exponent position. So there's a couple pictures here that are classic exponential functions where you have the base. Here's different choices of base. I have base 2, base 3, base 4, base 1/2. So these are just some common examples of exponential functions. The toolbox function, if you have a more complicated looking exponential function, the toolbox function is always going to be the base to x. So in this case, what I would say is I have 1, 2, 3, 4 different toolbox functions for 4 different exponential functions. Each choice of base gives you a different function, a different toolbox function. And the graphing techniques we found for doing transformations of toolbox functions, you apply them to b to the x, whatever the base is. So some important features on an exponential function. So this right here is an important feature. So what you see is that the vertical intercept, or the y-intercept, appears to be the point input 0, output 1, and in fact it's exactly what it is. And the idea is, and we've already seen this earlier this semester, that if you take a number and raise it to the 0th powers, I mean there's an exception, we don't do 0 to the 0, that's naughty, it's an indeterminate form. But if we do a non-zero number to the 0th power, we get 1. So 2 to the 0 is 1, 3 to the 0 is 1, 4 to the 0 is 1, a half to the 0 is 1, and in general for any exponential function, because we are raising non-zero numbers to the 0th power as we cross the y-axis, the output's always going to be 1 there. So this is a common feature. Every exponential function contains the point 0, 1. The other key feature on these is the horizontal asymptote. So you can see right here the x-axis is a horizontal asymptote for each of these exponential functions. The x-axis is a horizontal asymptote. And all that means is that the x-axis forms a horizontal line that the function outputs approach or get as close as you want them to get to that line. This is the line, the x-axis is the line y equals 0. So the exponential functions get as close as you want to the line y equals 0, but they never touch it. They never cross it. And an exponential function will never output a 0 unless you apply a transformation like 2 to the x minus 5, where you drag the entire graph down 5 units. But the toolbox function will never take on the value y equals 0. So we get a horizontal asymptote that the function approaches but never touches. The other key feature is we see these exponential functions are all going to infinity for their outputs. And if we look carefully at any one of these, we see that the domain is negative infinity to infinity. And in fact, that's actually driven home right here in the definition. X can be any real number, which means x will go from negative infinity to infinity. So what we could say is that the domain of an exponential function, an exponential toolbox function, is going to be any real number you want, so negative infinity to infinity. We see that we have a horizontal asymptote at y equals 0. So the function never gets to 0. So y is going to be an element of, hey, I never get to 0, and I go to infinity. And the end behavior is going to depend a little bit on the shape of the graph, but it's always going to do one of two things. It's either going to, as x goes to negative infinity, either y is going to go to 0 or y is going to go to infinity. And we see that here, right? These functions, 4 to the x, 3 to the x, 2 to the x, are all going to 0 as x goes to negative infinity. This function, though, as x goes to negative infinity, is actually going to infinity. And the other possibility is, for end behavior, as x goes to infinity, either the y values are going to go to 0, like they are for this function right here, or the y values are going to go to infinity. So that's basic intro to exponential functions. What we want to do next is explore the relationship between 2 to the x and 1/2 to the x. And what we want to notice here is that the base 2 and base 1/2, we're actually looking at bases that are reciprocals of each other. So this function right here, this is the function f of x equals 2 to the x. And this function right here, this is the function g of x equals 1/2 being raised to the x power. And when you look at those, what you ought to notice, or what you hopefully notice, is that it looks like they have even symmetry. It looks like they are symmetric with each other in the y-axis, or the vertical axis. It looks like 2 to the x and 1/2 to the x are just reflections of each other in the y-axis. And in fact, they are reflections of each other in the y-axis, and we want to take a moment to think about why this is. So it's actually pretty simple to explore. If we have the function 1/2 to the x, we want to recognize that this is really 1 over 2 to the first power being raised to the x. And from our exponent rules, we know that we can move a number up or down into the numerator, up into the numerator, or down into the denominator by changing the sign of the exponent. So I could take this 2 to the first and raise it into the numerator position if I put a negation on the exponent of 1. And this was something that we had explained conceptually earlier in the semester. So I wind up getting 2 to the negative first to the x. And then what we want to remember is that when we have one exponent being raised to another, we can simplify that by multiplying those exponents. So negative 1 times x is just negative x. And we want to look at g of x equals 2 to the negative x, and think about it for a moment in the context of what we have learned about function transformations. So what we have learned about function transformations is that when you put a negation sign on the input variable, that it indeed reflects the function, the toolbox function, over the y-axis. So if I have a base 2 being raised to negative x, or the opposite of x, this is just a reflection of 2 to the x in the y-axis. And in general, if we have 1 over b to the x, this is just the same as 1 over b to the first to the x, which is just the same as b to the negative 1 raised to the x, which is b to the negative 1 times x is negative x. So 1 over b to the x, what we see is that it is just the reflection in the y-axis of b to the x, because we have the negation on the input variable x. So the relationship between b to the x and 1 over b to the x power for an exponential function is that they will always be reflections of each other in the y-axis, or the line x equals 0. So looking at how to graph transformed exponential functions. So these are going to follow all of the function transformation techniques that we've already learned. And in general, the expectation that I have is that you write down explicitly what the transformations are, and then you apply the transformations. I think on the last test where people needed to transform functions, students just gave me the transformed picture without telling me what the transform steps were, and so that gets marked down on the exam. We want to make sure that we list the transformations. So let's look at the function that we have. We see that 2 is in the base position. So the toolbox function is going to be f of x equals 2 to the x. And then our technique for drawing transformed functions is to get some key lattice points on the toolbox function. So here I have already done 2 to the x using GeoGebra and just took a screenshot of it. So how did I generate these key lattice points? Well, I just plugged in some easy, simple values for x. I plugged in x equal to 0. I got 2 to the 0 is 1. So input 0, output 1. And then I saw that 2 to the first power, we put a 1 in here. 2 to the first power outputs a 2. And if I put a 2 in for x, if I input 2 for x, I get 2 squared, which is 4. So I generated for myself 3 nice lattice points just by plugging in 0, 1, and 2 as inputs for x. And I chose those because they were easy to work with. So to graph this, I just want to list the transformations. So remember, first we look at what are the horizontal transformations. And to look at horizontal transformations, we ask the question, is anything being added or subtracted from the x, from the input variable? And yes, 1 is being subtracted. Sorry, 1 is being added to x. So this is going to take the graph of the toolbox function and move it 1 unit to the left. So we're going to move 1 unit left. 2, do we have any reflections? In other words, is there a negation on the input variable? No, there isn't. Or is there a negation on the outside of the toolbox function? Is there a negative sign being attached in front of the 2? And in this case, no. So there's no reflections. There's no stretch, because we're not multiplying the toolbox function by anything. We don't see something that looks like 3 times 2 to the x, where we're getting a stretch. There's no negation where we're getting reflection over the x-axis. There's nothing being multiplied to the exterior of the toolbox function. So no reflection, no stretch. And then right here we see we have a transformation or translation of 3 units down because we're subtracting 3. So we need to go and move 3 units down, or vertically. And because there are no reflections or stretches, we really have just a 2-step transformation process. Move 1 unit to the left, move 3 units down. Again, on exams, I want you to explicitly list in the correct order the transformations that have been applied to the toolbox function. All right, so let's go ahead and apply our transformation. So 1 unit to the left means take each lattice point that we have and move it 1 unit to the left. And then each lattice point gets moved 3 units down. So 1, 2, 3 moves 3 units down to the point 1, 1. I'm labeling it because it's the final point. Moves down 1, 2, 3 to the point input 0, output -1. Moves down 3, 1, 2, 3 to the point -1, -2. And so the other key thing that we need to do that we haven't had to do before is we also need to transform the horizontal asymptote. So we have the horizontal asymptote for the toolbox function, which is the x-axis or the line y equals 0. And the key is that the vertical transformation gets applied to the horizontal asymptote as well. So not only does the function move down, but its horizontal asymptote must move down the same amount that the function moves. So the function moved down 3 units. So the horizontal asymptote, which started at y equals 0, is going to move down 3 units and become the line y equals -3. And so when we graph this, the exponential function is going to, me trying to draw a graph using the pen pad is always an exercise in futility. Try this one more time before I give up. Sweep along the horizontal asymptote. Pick up the points. Ooh, smoothly pick up the points. No, don't do this to me. No, I have to try it a third time. I can't give up after that. I have to try one more time. If I fail now, then we'll just pretend that I did a nice job. You got to sweep through, pick up those 3 points, and it's going to go off to infinity. That's still really horrible, which is why we like graphing utilities. The point in, I think the point in having a person hand draw some of these is it's nice for us as users of mathematics to be able to look at a function, kind of understand what the toolbox function is, and recognize that transformations have happened. And it gives us an ability to mentally see where the function is without even needing to graph it. So domain and range. Domain, you can see it's still going to go from -infinity to, hey, I have an up arrow. X is still going to go from -infinity to infinity. And the key idea here is that if the domain starts off as -infinity to infinity, and all you do is move the function to the left or right and up or down, it's not going to change the function's domain. The range is going to change, however, because remember the toolbox function. Where did y go on the toolbox function? Well, he went from 0 to infinity. And we did have a vertical transformation. So the domain always moves vertically. It's identifying outputs. So if a function has a domain, that domain shifts with the function as it transforms. So we went from 0, we went down 3, so this is going to go down to -3, which is the location of the new horizontal asymptote. So the domain of the toolbox function gets shifted. It started at 0, but now it gets shifted down 3 units to a new location. We did move 1 unit left, but if you move 1 unit left, -infinity gets moved 1 unit to the left, positive infinity gets moved. I mean, that doesn't do anything to infinity. Shifting it, if our bounds are -infinity to infinity, horizontally shifting by 1 unit left or right isn't going to change that domain. All right, one more example. So again, the toolbox function, I see I have base 2. I see that I have a base 2, so my toolbox function is going to be f of x equals 2. If there were a 3 here instead, then my toolbox function would be 3 to the x. It's 2 to the x is my toolbox function. If it was 4 to the negative x plus 2, then my toolbox function would be 4 to the x. So you just look at the number in the base position, and that establishes your toolbox function. Once you establish the toolbox function, list the transformations. Hey, nothing is being added or subtracted from the x, so there's no horizontal translation. There's a negation on the x, so there is a reflection in the y-axis, a y-axis reflection because of the negation on the input variable. No stretch, no reflection over the x-axis, and no stretch because nothing is being multiplied to the 2 to the negative x. It's really just a 1 times 2 to the negative x. So nothing's happening out there. And then the graph is moving up 3 units. So to transform this function, then we would take our lattice points, find them just like we did before by putting in nice values for x. It says reflect in the y-axis, so this one is stuck. This one's going to reflect over to here. This one's going to reflect over to here. And then we have a plus 3, so we have a vertical movement by 3 units. Move up from here, goes up 1, 2, 3. So he winds up at negative 2 and 7. This one moves up 3. 1, 2, 3. He winds up at input negative 1, output 5. This one moves up 3 and winds up at 0, 4. And the horizontal asymptote, which was at y equals 0, has to move up 3 as well. So it moves up to y equals 3. Right, this was y equals 0, so the new horizontal asymptote is going to be y equals 0 plus 3. We translate it 3 units up. So there's the new horizontal asymptote, and then it's just a matter of attempting, probably unsuccessfully, to draw this is where I should take some drawing classes. I wonder if there's a drawing class that goes into how to draw mathematical equations better. So that's better than the last one, I think. So domain, again, because the domain of the toolbox function went from negative infinity to infinity. Here's my toolbox function. When I reflect, that's not going to, the only horizontal change that happened was a reflection on the y-axis. That isn't going to change anything. Put a negative on here, you get negative infinity. Negative infinity becomes positive infinity. X is still going to be running from negative infinity to infinity, but the range is going to change because we moved up 3 units. The toolbox function, his range was from 0 to infinity, but now we have to add 3 to that 0, so the new range is going to be y is an element of the open interval from 3 to positive infinity.